All right, picking up on the discussion of London dispersive forces or London dispersion forces, we saw the kind of explanation of induced dipole as it happens in helium. What we really need to take into account when we're thinking about how these types of forces affect physical charges, not physical charges, physical properties, is the way in which the size of the atom or how strongly the electrons are held within the atom affect how strong this charge can be. So when we talk about electrons being a little more easy to displace, that's a property called polarizability. And we've seen as you go down the periodic table, even though the nuclear charge is going up, the outer electrons are shielded from experiencing that nuclear charge. So as shells of electrons get further and further away from the nucleus, it becomes easier to distort their shape, to move those electrons around a little bit. And we can kind of see that in the trends here. So I have a couple trends here on the page, and we're just going to talk about BP here is the boiling point. So we already mentioned helium has a boiling point of 4 Kelvin. I'm going to put that into Celsius here for this particular chart. So helium boils at minus 269 degrees Celsius. Now, as we go down the noble gases, or column 8 in the periodic table, and we drop down to neon, what's different about neon is there's one more layer of electrons. Neon has filled the second energy level with electrons in addition to just the first, as in helium. So there are not only more electrons in neon, but the ones on the outside are less strongly held. It's a little easier for the electrons to deform, and as a result we get stronger London forces between neons. So when we go to neon, the boiling point goes up, indicating it takes a little more energy to break two neon atoms apart, separate them from the liquid phase into the gas phase. And what we see is this trend increases as the atoms get larger and larger. So you go to argon, and the boiling point goes to minus 186 Celsius. For krypton, it's minus 153. For xenon, it's minus 108. Right, all still gases, but we can see that the strength of the interaction is going up. So as the atoms get bigger and get more polarizable, they have stronger London dispersion forces interacting between them. Now, in terms of the inert gases or noble gases, element 118 has been named oganesson. I don't have it on my chart. And it doesn't last very long in terms of stability, so it's not like you can get a sample of it and measure the temperature at which it's boiled. But it's estimated that the boiling point will be 350 Kelvin, which would mean if you could have a sample of oganesson or element 118, it would be a solid at room temperature. So 350 Kelvin would be about 77 degrees Celsius. So if it wasn't radioactive and decayed in a few seconds, it would potentially be a solid, even though it would still be part of the noble gases or inert gases. Now, lower down here I have the halogens, so diatomic molecules, fluorine, chlorine, bromine, iodine. Right? And we see a similar trend here. Fluorine is a very small atom. It holds its electrons really tightly. So there's not a lot of area in which one molecule can overlap with a nearby molecule. So for F2, the boiling point is 188 degrees C. So fluorine would be a gas, right? And at really low temperatures would still be a gas. Now chlorine, the molecule, the atoms within the molecule, and so the molecule itself are getting larger. Those electrons are also a little easier to deform. They're a little more polarizable, so still a gas, but the boiling point is going up closer to room temperature. Right? You add another layer of electrons to make bromine, and you have your diatomic bromine molecule. The boiling point now is above room temperature. So bromine is actually a liquid at room temperature, and you need to go a little bit above room temperature to see it start to boil and turn into a gas. And iodine compound gets even bigger. Iodine is a solid at room temperature, and it's not going to boil until you go up to a much higher temperature, 184 degrees C. Now, there's one more halogen there, which is astatine. And you don't talk about astatine a whole lot because it's radioactive and it's not very abundant, so it's not particularly useful in any laboratory sense. But you see the trend continue. The boiling point for astatine in the diatomic form would be 337 degrees Celsius. So there's a couple of trends here that we need to think about in terms of applying how London dispersion forces affect boiling point. More electrons is going to tend to lead towards a stronger set of interactions, but there's a polarizability effect there too, which is how easy is it to move those electrons around. Really electronegative elements are going to be a little less able to have their shape deformed than less electronegative elements. So things like fluorine tend to not have very strong intermolecular interactions. That's why something like a Teflon surface won't stick to things, because fluorine just doesn't interact with things around it. But larger atoms is going to be a little easier for them to interact. So one more example here, in terms of London dispersion forces that I think is relevant, is that the surface area of a molecule can have an effect here as well. And if we think about just two examples here, if I have a molecule that has 5 carbons, I can imagine one structure where those carbons are kind of connected in a line. Now I'm zigzagging the line because I know these carbons are going to end up being tetrahedrals, so all the angles are going to be 109.5 degrees. But 5 carbons, you could have 12 hydrogens. So the carbons kind of in the middle of the chain would each need 2 hydrogens. The ones on the end would each have 3. So one structure you could draw for this would be C5H12 would look like that. Now we can draw another structure too, where I put 1 carbon in the center and I make 4 bonds to the other carbons around it like that. Exact same atomic composition as the first one, but a different structure, right? So these same formula, these are isomers of each other. Carbon-hydrogen bonds carbon and hydrogen are very close in electronegativity, but they're also generally tetrahedral structures. So carbon-hydrogen compounds are generally considered to be non-polar. So it would just be London dispersion forces that are acting in these molecules. So what's going to affect which one has a higher boiling point, which one has a lower boiling point, would be how much surface area there is where the molecules could interact. If you think about the surface of this molecule, it's a lot more spread out than the surface of this molecule, right? In fact, we're just kind of looking at a two-dimensional representation, but you can see the effect here. If you bring another molecule close, they can't really overlap a whole lot. So there's a much weaker set of interactions in this version of C5H12 than there is here, where another molecule can kind of snuggle up, and there's a lot of space, surface area, where the molecules can interact. So the first molecule here is called Pentane, and its boiling point it's a liquid. I don't know the exact boiling point, but it's a liquid at room temperature. Boiling point is probably around 60 degrees Celsius or something like that. This molecule, the common name is neopentane or new pentane. This molecule boils at about 20 degrees Celsius, which means right at room temperature, it is converting from liquid to gas. In fact, I used this compound as a solvent when I worked in industry, and you could actually feel it boiling as you grab the bottle. The heat from your hand would cause it to start to boil, and you could feel the bottle getting cold as you grabbed it from the enthalpy of that phase change. You could actually see it boiling as you pick it up and are holding on to it. And that's just a function of the surface area of the molecule. So as we're thinking about intermolecular interactions, that's something else we'll need to think about, and we'll stop there and we'll continue chapter 10 in the next video. And that's also the next note document.